the pace is now picking up and explaining what the atom looks like. Niels Bohr, he applied Einstein's and, of course, Newton's concept of light as quantized photons. Well, actually, Newton just said they were particles. Einstein added the quantized bit. This was applied to the Rutherford model to explain the optical spectrum for hydrogen-like atoms. Now, what's a hydrogen-like atom? These are atoms with only one electron. So hydrogen, of course, fits the bill. It only has one electron. Helium, if it loses one electron, so it's now a positively charged ion, that would be a hydrogen-like atom. Lithium would have to lose 2 electrons, etc., etc., up the periodic table. And he obtained good agreement with experimental data. Now, despite only having one electron, hydrogen emits many different wavelengths of light when it is excited. And this is what Bohr explained with his model introduced in 1913. So, let's start with these optical spectra. A quick review of optical spectra. When light is passed through a diffraction grating, and this was covered in the EM waves unit of this course, interference causes different colors of light to show up on a screen past the diffraction grating. This is an example of energized xenon. You have xenon gas in a tube. You put an electric potential on it, just like the Crookes tube. The xenon gas will emit light with frequencies that are unique to xenon. It's a fingerprint for xenon gas. No other gas would show this pattern. When this light is passed through a diffraction grating, it shows this optical spectra. The Rutherford model had no explanation for this. Here's the spectrum from ionized hydrogen gas. This is important because this has been well studied, and equations were derived to explain the positions of these various wavelengths, these various colors, that would fit the spectra. So in other words, I came up with equations without a theory. They'll be shown on the very next page. And you can see here, this section here is the visible light spectrum, and this BA up here represents Balmer, the physicist who came up with it. Then you have light in the ultraviolet, and then you have light down here in the infrared. And these are all peculiar to hydrogen. No other element has this spectra. These are the equations that I just talked about on the previous slide. 1 over the wavelength of light equals R, which is the Rydberg constant, 1.0974 times 10 to the 7th inverse meters. And this n over here was experimentally determined. They found that they could find the positions of all these wavelengths by plugging in this quantity n without really saying what it is yet. This is the visible spectrum. You can see these wavelengths. That's the Balmer series. Then Lyman came up. He found these. Paschen found these. And again, absolutely amazing. There were data. These equations were fit to the data, and they predicted the other lines and matched them exactly. And again, let me just circle this N for emphasis. Really not quite sure what that is yet. Another issue that Bohr needed to address was the planetary orbits of the electrons. Now, the electrons in the Rutherford model were kept in orbit by the Coulomb force, so let's put the nucleus here, and here's the electrons out here, obviously not drawn to scale. Negative, positive, attractive force due to the Coulomb force, and since the electrons are going in a circle, so at any one point their direction there is tangent to the circle, the force is inwardly direction. So that Coulomb force gives you the centripetal force necessary to keep the electrons in orbit. That's good. However, shown earlier in the 19th century, an accelerating charge, and again, these charges continue to accelerate, right? They keep a constant speed, but their velocity is always changing. I hope you remember that from mechanics, because the velocity is a direction, any magnitude, and the direction keeps changing, so there is an acceleration. So if these electrons are accelerating, they're going to emit electromagnetic radiation, and since they're constantly accelerating, they will continually lose energy. If this energy keeps being lost, the electrons will slow down, they'll fall out of orbit, and collapse into the nucleus within 10 to the minus 11 seconds. This obviously doesn't happen since we're all still here. Here's what Niels Bohr said. It is still called a semi-classical model because he's combining classical physics with some aspects of the emerging quantum world. 1. Electrons can only revolve around the nucleus in specific circular orbits with fixed angular momentum and energy. The further away from the nucleus, the greater momentum and energy of the electrons in these orbits. And here's the key point, which he just made the statement. When in these orbits, the electrons would not radiate electromagnetic energy. So that takes care of the problem of the electrons falling into nucleus. Although you might ask how he could say that. Well, he just did. And then the equations he came up with predicted what would happen. Energy is emitted, and here's where we start talking about the spectra of the atoms. It's emitted from the atoms in the form of light when electrons move between orbits, and we'll have a picture of that coming up. And not a continuous spectrum of energy. The energy would be quantized, just like the photoelectric effect, just like black-body radiation. Only photons of particular energy would be emitted, and they would represent the energy difference between the allowed orbits. And again, we will have pictures on that coming up shortly. Here's the picture of the Bohr atom. Right in here, this little yellow guy here, that's the nucleus. And then we have these orbits, these planetary orbits, n equals 1, n equals 2, n equals 3. Each one refers to one of these circular orbits. And these n's, earlier we showed the equations for the spectra with the Rydberg constant. It's the same n. What we have is here's an electron in the n equals 2 orbit. And notice, electrons can only be in the orbits. There can be no electrons, for example, right here. Not allowed. Has to be in one of these orbits. If an electron drops from n equals 3, which is a higher energy orbit, down to n equals 2, it will release a photon. And that photon will have energy E equals hf, the same equation we've been using for the past several chapters. And that energy is equal to the energy difference between the two levels. Based on Bohr's assumptions, we come up with some math. The angular momentum of each level is different, and it's quantized. Okay? There's only specific values allowed. N is the number of the energy level, and the angular momentum is equal to mv r sub n. And then we substitute in, we get h over 2 pi. That's the value of Vr. I'm not going to go through all the math here. This is kind of a shortcut. So the angular momentum is n h over 2 pi when n equals 1, 2, 3, etc. However many orbits there are for the electrons. The Coulomb attractive force between the nucleus, which has a charge of Ze, where Z is the atomic number, tells you how many protons there are, and the single electron that provides a centripetal force. Now remember, we're talking about atoms that only have one electron, so helium would have had to have been ionized and lost one of its electrons. So we have Coulomb's law, K QQ over R squared. One charge is the nucleus. This is the single electron. Calculate it out, and we get the Coulomb force is mv squared over r sub n. That's providing the centripetal force. So we have k ze squared over r squared equals mv squared over rn. That's the right side of Newton's second law for centripetal acceleration. Continuing on, we combine the equations from the previous page, which use Coulomb's law and angular momentum, and we do a little algebra. It really isn't much, so this looks far more complicated than it actually is. We find that the radius of an atom is equal to n of an orbit is n, which is the orbit number. Here's Planck's constant. Here's pi. Here's the mass of the electron. Here's k, Coulomb's constant. Z is the charge on the atom, or how many protons you have, and E is the elementary charge. Next equation, again, no one's ever going to hold you accountable for this at this level yet, tells you the energy level of these various orbits. And for that, we've basically used the equation for kinetic energy, potential energy, angular momentum, Coulomb's law, Newton's second law, and Bohr's quantum assumption. You do all that work, and you find the energy level of an atom with number of protons Z, n is the orbit that you're talking about. And you've got this little negative here. Don't worry too much about that. That just means that this is an attractive force and the electrons stay connected to the nucleus. The previous slide may have looked a little daunting with all the letters and numbers, but fortunately for us, most of those letters were constants. So when we plug those constants in and solve for, let's say, the ground state of hydrogen, and the ground state is where n equals 1, it's the first orbital, z equals 1 for hydrogen, that big equation for the radius of the atom, radius of the orbital, all cranks down right here. So the ground state of hydrogen, the radius of the first orbital is 5.29 times 10 to the minus 11th meters. And that's actually given a name, that's the Bohr radius. In general, when we come up with the radius, again from the equations from the previous page, the radius of any hydrogen-like atom is just n, where n is the orbital we're interested, n squared divided by z, which is the atomic number of the atom, times the Bohr radius. So that big equation from the previous page shrinks down to this. And even better, the energy equation, which had a lot more terms, when we just substitute in the values of the constants, we're left with E is minus 13.6 eV. And by the way, an electron volt, it's just another unit for energy. It's equal to 1.6 times 10 to the minus 19th joules. We use it when we're talking about atomic physics and then later nuclear physics because it's easier to handle. We don't have to worry about exponents and it just makes it look a little prettier. So the energy level is negative 13.6 eV times z squared over n squared. So those big equations from the previous page have collapsed into some rather simple equations. And again, the negative sign just tells you that the electrons are bound to the nucleus. The true test of any theory is, does it match reality? Does it match experiments? And absolutely in this case. These calculations from Bohr are in excellent agreement with the optical spectra showed earlier, also in excellent agreement with the Rydberg constant equations that people just experimentally determined. The next slide is going to show the various transitions between these quantum levels, n equals 1, 2, 3, etc. for hydrogen, and they've been named for the physicists who first observed them. As said earlier, the Balmer series of orbital transitions are the only ones that are in the visible spectrum. This is the hydrogen atom, and you can see the orbitals. Here's n equals 1, that's the ground state, no excitation energy there. Here's n equals 2, which is the first excited state. And I'm sorry about that the n equals 2 level is the first excited state, n equals 3 is the second excited state. And then these lines here, for example, this shows an electron starting at the n equals 6 level, dropping all the way down to the n equal 1 level. So that's a very high energy transition, so it has a very short wavelength, right here, 94 nanometers. Okay. Here's the Balmer series, and you can see the wavelengths of the electromagnetic radiation. These are all in the visible spectrum, 410 nanometers, 656. 656 nanometers, that would be from n equals 3 to n equals 2. So up here, this was the Lyman series. Here's the Balmer series. And you can note that all the Balmer series transitions are ending in n equals 2. The Lyman all end in n equals 1. Then you have the Paschen series all end in n equals 3. All these wavelengths have been measured. All of them agree with both the Rydberg constant equations, and they also agree perfectly with the Bohr model.